So very good morning. So in the last class, I have explained about about the summary of the BJT and the applications of the BJT. It is BJT as a switch and the BJT as as an amplifier. Okay. And in this class, we are going to see about the operating point and the DC load line here. Okay. So in this class I am going to explain it is what actually the DC load line and what is the it is a DC operating point and what and the representation of the Q point in the active region and in the cutoff region and in the saturation region, and what do you mean by the stability factors. And what are the factors affecting the stability of the Q point, and it is what are the methods to stabilize the variation of the IC. So all these is going to be studied in this class here. Okay, so if you take the DC load line and the DC operating point, okay, suppose consider it is what the graph of the BJT. So along the x-axis, it is going to consider the output voltage here. The output voltage in this case is an VCE, and along the y-axis it is going to consider the output current. The output current in this case is an IC. So it is the graph of the, it is VCE versus the IC here. Okay, and it is towards the what the x-axis, so that IB is going to be the 0. So if the transistor is in the, it is what open switch, it is going to be operated in the cutoff region here, so that you can able to see the, it is a dotted, it is a line, it is a shaded part here. So it is an output characteristics here. And if you take along this shaded part here along the y-axis here, and in this case what this IB is going to be the maximum, and in which the output current is also, it is going to be the maximum, and it is what this region is called as the saturation region. And if you take the region in between the cutoff and the saturation is called the active region, in which the variation of the IB, it is going to vary the IC current here. Okay, this is the characteristics here. So it is already studied in the previous semester. It is while studying the output characteristics of the BJT. Okay, so along the x-axis it is having an output current, it is an VCE, and along the y-axis it is having an output current, it is represented as an IC. And if you take this okay, shaded part is called as the cutoff region, and if you take this part is called as the saturation region, and in between the cutoff and the saturation it is having the one more region, this is called as an active region. Okay, and after that you can able to see the one line here, this is itself is called as the DC load line. Okay, and you can able to see the points on the line here, it is what A, R, Q, P, B, etc. So all those points on this line is called as the DC operating point here. Okay, so and it is as per this diagram is to be considered, it is for the different biasing voltages. Okay, the different points of the operations are obtained. So I said in the previous class that it is biasing voltages has to be applied in order to operate the transistor as an amplifier. Okay, if it is having the different biasing voltages, if the biasing voltage is going to change, according to that it is going to appear the different points P, Q, R, etc., etc., are called as an operating points. And if you draw the line on these points, what is itself is called as the DC load line. So what the locus of such points is called as the DC load line. If you take the what end points, it is the two end points are the VCC comma 0, it is on the x-axis. so that you can able to see what this point A, it is in which the value of the it is y-axis is equal to 0, and it is to be represented as VCE is equal to VCC, or it can also be represented as the VCC comma 0. And if you take the other end of the line, which is indicated as an IC is equal to VCC by RC, or it is also indicated as of the 0 comma IC. It is because on the B the value of the x-axis is equal to 0 here, so which is to be represented as of the 0 comma IC, and a line passing this through these points is called as the DC load line. If you draw the line on this point is called as the DC load line, and each point on the load line is called as the DC operating point. So any of the point existing on this line itself is called as an operating point, and it is what this operating point is also called as the quiescent point or the Q point. And if you take the value, okay, so if you take the value of the VCE and ICE is expressed as the point as x comma y is equal to VCEQ comma ICQ. So what this the x value VCEQ is, it is the point on the x-axis, and what this y, it is to be concerned to the y-axis. What this q is indicating, it is the quiescent point or the operating point here. And in order to get the faithful amplification, what this q point, it must be selected properly. Okay, so this is all about, it is a DC load line and the DC operating point here. Okay, so again I am going to repeat. If you draw the graph, okay, of the VCE versus IC, and the VCE is along the x-axis, IC is along the y-axis, and what this shaded part is called as the cutoff region, and what this shaded part is called as the saturation region. In between the cutoff and the saturation, it is having an active region. Okay, so in between it is having an active region, and in this case, if you draw the line here, okay, this itself is the DC load line here, and you can able to see what this point A and the point B are the two end points. What this point A is indicated as of the VCC comma 0, and what this point B is to be indicated as of the 0 comma IC here. Okay, and so if any of the point existing on these lines itself is called as, it is a DC operating point, or it is also called as the quiescent point or the Q point. And for the faithful amplification, so this operating point is to be chosen properly here. Okay, so and we'll see now, it is the operating point in the active region. In the active region means if you choose the operating point in this part here. Okay, so if the operating point, if the operating point is located in the active region in the middle of the DC load line, okay, what this sinusoidal waveform is, it is without the distortion is obtained at the output here. Okay, so that you can able to see, it is the graph of the VCE versus the IC. It is an output voltage versus output current, and you can able to see it is the point Q exactly on the middle of the line here. You can able to see this is the DC load line, and it is exactly middle of the point, and in which the operating point, what this Q point is in the active region. In the active region means it should be in the middle of the DC load line. In the middle of the DC load line. If it is in the middle of the DC load line means, so if you apply the sine wave as in this way, okay, it is going to give you the complete sine wave here. Okay, this is an IB current, it is an input current, and you can able to see this is an output current, and in this you can able to see this is an output voltage here. Okay, so it is whatever the input has been applied, the entire signal is going to be appear at the output here. If you choose the Q point in the active region in the middle of the DC load line. Okay, and if you choose the Q point, it is which is near to the saturation. If it is near to, if it is near to the saturation region means it is nearer to the y-axis here. Suppose consider that if this is the DC load line, and if you observe the operating point, it is nearer to the y-axis. If it is nearer to the, if it is near to the y-axis means, so that you can able to see, so any of the signal appearing above the maximum point is going to be clipped off, it is going to be eliminated here. So in the output it is going to get, it is some of the distorted signal, so it is going to be eliminated, it is going to be cut off here. Okay, in the same way, if you choose the operating point, it is nearer to the cutoff region, if the collector current is to be clipped at the negative half cycle, because the transistor is driven into the cutoff. So if you take this DC load line, if you choose the cutoff point which is nearer to the, if you choose the operating point which is near to the cutoff region means, it is going to clip the negative part of the signal here. So it is going to be eliminated, so that you can able to see the dotted line, it is going to be clipped off here. So if you apply the input signal as in this way, so that you are going to get the output as in the clipped manner here. So this IB is the input current, IC is the output current, and VCEQ is the output voltage here. Okay, understood? So in this case, important point to be remembered is, so if the Q point is in the exactly middle means, the entire signal is going to be appear at the output here. And if it is nearer to the saturation means, it is going to clip the positive part of the signal here. And if it is nearer to the cutoff region means, it is going to clip the negative part of the signal here. Okay, this is about the operating point if we choose at in the active, in the saturation, and in the cutoff region here. Okay, and if you see the definition of the stability factor, okay, what this stability factor, it is going to be dependent on the output current and the voltage VPE and the gain beta. So if you take the rate of change of the collector current with respect to the collector, this leakage current ICO is called as the leakage current at the constant VPE, and the beta is called as the stability factor. So that you can able to see it is to be represented as S is equal to, it is a delta IC. What this delta IC is, the change of the collector current, which is equal to, it is equal to delta IC2 minus it is delta IC1. It is a change in the output current. It is the first current obtained, it is the second time obtained value, and if you take the difference, so that you can able to get the change of the collector current value. And what this delta ICO, it is the leakage current, so which is equal to delta ICO2 minus it is delta ICO1. If you obtain the difference of this one, so that you can able to get the delta ICO, in which the VBE, it is base to emitter voltage, and the gain, the beta, it is going to be the constant here. VBE and the beta is going to be the constant, and it is going to give you the stability factor. Yes. And if you take the one more stability factor, it is what the S dash, in which it is the change of the collector current, it is with respect to VBE, it is the base to emitter voltage. This is the base to emitter voltage. The output current is to be changed, it is with the change in the base to emitter voltage, in which ICO, it is a reverse leakage current, and the beta is going to be the constant here. And if you take the, it is one more stability factor, S double dash, it is the rate of change of collector current with respect to the beta at the constant ICO and VP is called as the stability factor S double dash, in which the IC, it is a delta IC divided by, it is a delta I, it is a beta, in which what this delta beta is equal to, it is beta 2 minus beta 1 value, it is going to give the change in the beta here, at which the ICO and the VB is going to be maintain the constant. So for that purpose, what this stability factor, it is going to be dependent on the leakage current, it is VBE and the gain. So if the output current, it is delta IC, and the delta IC. If the output current is going to change, it is with respect to the leakage current, it is indicated as the yes, in which VBE and the beta is constant. And if the output current is going to change, it is with a change in the VBE at which the ICO and the beta is constant, it is called as a S dash. And if the output current is going to change with respect to change in the gain, it is delta beta at which the ICO and VB is constant, is called as an S double dash. And if you take the entire total change, and it is to be given by the formula as it is equal to delta IC is equal to, it is S into delta ICO plus S dash into delta VBE plus S double dash into delta beta. This is the entire total change of the output current is with respect to leakage current, with respect to base emitter voltage, and with respect to the gain here. This is about the stability factor here. And if you take the factors affecting the stability factors, so what it is, what this Q point depends on the collector current IC. So if you take the factors which affect the ICR, it is reverse saturation current ICO, it is base emitter voltage VPE, and the current gain beta. So it is the factors which is going to affect the stability factor. So it has been seen in the formula here. This is with ICO, with VBE, and with beta here. So it is with the reverse saturation current, with the base emitter voltage, and the current gain here. Okay. So if it is with respect to the reverse saturation current means, suppose consider that it is what the change in the output current, it is with respect to, it is reverse saturation current. So if you take the collector current, it is to be given by IC is equal to, it is beta into IB plus, it is beta plus 1 into ICO here. What this ICO, it is called as, it is a reverse, it is saturation current here. So it is when a PN junction is under the reverse bias, okay, there is a small amount of the reverse current, it is due to the flow of the minority carriers across the junction. And what this reverse saturation current ICO is going to double for every 10-degree rise in the temperature. Okay, and what this flow of the collector current produces the heat at the collector junction, and what this increase in IC increases the temperature of the collector junction, which increases the ICO again. And what the effect is cumulative, and at one stage IC is so large, it is which damages the transistor. And what this process itself is called as, it is thermal, okay, run away. So in this case, what happens here? So if the ICO increases, okay, IC value is to be dependent on the ICO. Increasing in the ICO increases the IC here. So increasing in the ICO increases the value of the IC, and increasing in the value of the IC increases the PD. PD is, it's nothing but its potential difference. So the voltage across the junction is going to increase, and if the PD increases, it increases the heat, it is going to produces the heat here. So increases the heat means it increases the temperature, and increasing in the heat or increasing in the temperature, again it is going to increases the minority charge carriers, so increasing in the ICO, and again increasing in the ICO increases the IC, etc., etc. It is going to be cumulative here, and at one stage it is going to generate the large amount of the IC, and it is going to damage the transistor. This is called as, it is thermal runaway. Understood? So it is what this reverse saturation current ICO, this IC output current is equal to, it is beta into IB plus, it is beta plus 1 into ICO. Increasing in the IC increases, increasing in the ICO increases the IC, increasing in the IC increases the potential difference, increase in the potential difference increases the temperature across it, increasing in the temperature again increases the ICO, and again increasing in the ICO increases the IC, etc., etc. It will be cumulative, it will be keep on adding. And if at one stage it is going to generate the very large amount of the IC, and it can able to damage the transistor here. Okay, this is one of the factor. It is going to affect the stability. Okay, this is the factors affecting the stability. It is one of the factor. And if you take the another factor, it is VBE. It is the base emitter voltage. Okay, VBE, it is the base emitter voltage. It is going to decreases at the rate of 2.5. It is microvolt. It is per degree Celsius. So that you can able to observe here. So increasing in the value of the VBE. So what this temperature has been decreased here. So indirectly, if the temperature has been got increased, suppose consider initially it is equal to minus 69 degrees Celsius, means its VB is equal to 0.4, and if it has been increased to 25 degrees Celsius, means its voltage is equal to 0.3. So the voltage has been decreased to it is 0.1, and if its temperature is equal to 100 degrees Celsius, it is equal to 0.2 here. So the base emitter voltage VBE is decreases by increasing in the temperature at the rate of 2.5 this microvolt per degree Celsius here. In the same way, if you take the one more parameter, it is beta. Okay, what this beta? Okay, it is going to increases its value on increasing in the temperature, so that you can able to see if you take the graph of the output current IC versus it is beta. It is for 55 degrees Celsius. It is minus 55 okay degree Celsius. What this beta value is somewhere around 10 here. And if you take for if the temperature has been increased here, okay, it is equal to 25 degrees Celsius. Its gain value is equal to 50 here. So increasing in the temperature from this minus 55 to 25, so its gain has been increased from it is 10 to this 50. In the same way, again, if you increase the temperature to 100 degrees Celsius, so its value of the beta is equal to 100, etc., in that way. So in this case, what this the beta increases with the increasing in the temperature. So its collector current IC is going to change here. So it is in this way it is going to affect. So what this reverse saturation current and what is base emitter voltage, and if you take the current again beta, it is going to vary according to the variation of the temperature here. Okay, so increasing in the ICO increases IC, increasing in the IC increases the potential difference, increasing the potential difference increases the temperature, and again increasing in the temperature increases the ICO. And in case of the base emitter voltage, so what happens here, the increasing in the temperature is going to decreases the voltage, but in the beta increasing in the temperature increases the value of the gain here. So in this way, the value of the ICO and the value of the VBE and the value of the gain, the beta, it is going to affect the stability factor. Okay. And if you take the methods to stabilize the variation of the output current IC. Okay, and if you take the methods to stabilize the variation of the IC, so in order to maintain the stability of or in order to maintain the variation of the output current, the constant. So in this you are using the two methods. One is it is thermal stabilization, and another one is it is bias compensation here. If you take the thermal stabilization, in this method, it is a resistive biasing circuits are used, which allow IB to vary so as to keep IC relatively constant with the variations of the ICO, it is VBE and beta. So you are using three configuration. It is fixed bias, it is collector to base bias, and the voltage divider bias. So what it is, the process of stabilizing the Q point is called as it is thermal stabilization. So I said that if the variation occurs in the ICO, or if the variation occurs in the VBE, or if the variations occurs in the beta, it is going to affect the IC current. So the variation of the IC takes place. In order to maintain the constant IC, along with this, the IB is allowed to vary here. If the variation occurs of the ICO, VBE, and beta. According to that, the IB is going to vary and the IC is going to be maintained constant. It can be done either with the fixed bias or with the collector to base bias or with the voltage divider bias here. Okay, and if you take the, it is one more, it is bias compensation in. So in this method, so what the, it is temperature sensitive devices, it is such as the diodes, it is transistor, it is thermistors, etc. are used, which provide the compensating voltage and the current to stabilize the IC with VBE and ICO. So if the IC increases unexpectedly, so it is to be compensated with the bias compensation circuit here, and it is going to be get decreased. And if the IC is going to decrease unexpectedly, and it is what is bias compensation circuit, it is going to increase the value of the circuit here. In this way, it can be stabilized, or it can be what is variations of the IC has been stabilized here. Okay, so in this class I have explained it is what do you mean by it is a DC load line, so that you can able to see this is the DC load line, and the existing points on this load line is it is a DC operating point. It is also called as it is quiescent point, or it is also called as it is Q point. If the Q point is in the active region, exactly middle means, so the what is the entire full signal has been obtained. And if the operating point, if it moves near the saturation means, it is some part of the positive cycle will be clipped. In the same way, if the operating point is moved, if it is near to if it is near to the cutoff, the some part of the negative half cycle is to be clipped off. And if you take the stability factor, it is to be dependent on the ICO, VBE, and the beta, and according to that, it is to be represented with the respective formulas here. And what the stability factor, so the factors affecting the stability of the Q point are the ICO, VBE, and the beta. In the ICO, what happens? Increasing in the ICO increases IC, again increases the potential difference, again increases the temperature, again increases the ISO, it will be cumulative. Okay, and the VBE is going to decrease. If the VBE is going to decrease, okay, it is with the increasing in the temperature. And what this, the beta is going to increase with the, it is decreasing in the temperature here. And if you take the methods to stabilize this, it is thermal stabilization. It is of the fixed bias, or it is collector to base bias, or the voltage divider bias. It is explained in the next class. And another one is of the bias compensation. It is going to provide the extra voltage is with the extra network here. So all this is, so if you say, if you take the sample descriptive questions about this is, so that he may ask you to define the operating point and it is a DC load line, or he may ask you to illustrate, it is illustrate the waveform. It is when the Q point is in the active region, in the cutoff region, and in the saturation region. Or he may ask you to define the stability factors, and he may ask you to explain the factors affecting the stability of the Q point, and he may ask you to describe the methods to stabilize the variation of the IC. So all these are the possible questions. Okay, and in the next class we are going to see about the voltage divider bias technique. Okay, so okay, thank you. Okay, thank you very much.